All right, welcome to the deep dive. We're going to tackle orthopedic embryology and the physis today, stuff that's like guaranteed to show up on your postgraduate exams.
Oh, yeah, for sure.
And we're using some awesome notes called Ortho Made Simple from mokyingren.sg.
Okay.
They were put together by Dr. Mokyingren. He's a sports surgeon over at National University Hospital in Singapore. And get this, he passed his FRCS in 2022. So we're in good hands, right?
Yeah, definitely sounds like it.
All right, so let's dive in. You're an orthopedic resident, so you know those exit exams are brutal.
Yeah.
But like, imagine you're sitting there and bam, a question about limb development. Way back in the early stages before a patient is even born.
Yeah, I see what you mean.
Think you'd be ready.
I mean, it feels kind of like going back to med school.
Totally.
But honestly, understanding this stuff is super important for figuring out those tricky clinical cases you'll see later on.
Absolutely. So how does it even happen? Like, how does a tiny little clump of cells turn into a fully functional arm or a leg?
So it all comes down to three main pathways, kind of like the boss is running the show. The AER, the ZPA, and the Wnt pathway.
Okay, I'm listening.
The ADR, or apical ectodermal ridge, it's driven by these fibroblast growth factor genes, and it basically sets the pace for how your limbs grow, from shoulder to fingertip or hip to toe. We call this proxima distal development.
So it's like the AER is laying down the blueprint for how long the limb will be.
Exactly. Now, imagine you're building a house.
Okay, I'm with you.
You wouldn't want the bathroom where the kitchen should be, would you?
Aha, definitely not.
That's where the ZPA comes in. The zone of polarizing activity, guided by the sonic hedgehog gene, makes sure your thumb ends up on the right side of your hand and your pinky's on the left. It controls what we call radial NAR development.
That's a great analogy. So if the ZPA messes up, you could end up with a thumb on the wrong side.
Well, not exactly like that, but it can cause things like radial club hand where the radius bone doesn't develop properly, or even like a duplicated thumb.
Wow, so even small problems in these pathways can have huge effects.
Absolutely.
What about the Wnt pathway? What does that one do?
Wnt, or wingless type, it's all about dorsiventral development. Think, back of your hand versus your palm. It makes sure everything develops on the right side, guided by the LMX1 gene. If this pathway goes wrong, you might see stuff like fibula hemimelia, where part or all of the fibula bone is missing.
Okay, I'm starting to see how these pathways all work together like a really precise dance. Each step has to be perfect to make a normal limb. But how do we actually get from a tiny little limb bud to a full arm or leg? It all starts around 4 weeks, right?
Right. At 4 weeks, it's just this tiny bud all about potential.
Yeah.
But by 8 weeks, all the major structures are there.
Wow, that's incredible.
It's like watching a building go up layer by layer.
It's amazing how fast it happens. So what's going on at the cell level during those 4 weeks?
So picture the mesodome as the construction crew.
Okay.
This middle layer of cells is what builds the bone, muscle, tendons, cartilage, all of that. Then the ectoderm, the outer layer, that becomes the skin, like the protective shell around everything.
So we got our limb taking shape, but what about the bones inside? How do they form? Cells don't just magically become solid bone overnight, right?
You got it. There are actually 3 ways bone formation happens: intramembranous, endochondral, and appositional growth. They each have their own steps.
Let's break those down. What about intramembranous ossification? What's the main thing to remember there?
Think direct transformation. Mesenchymal tissue, that's the loose connective tissue, it changes right into bone. It's how we get the clavicle and the flat bones of the skull.
Oh, okay.
What's cool is it's the same process we use in distraction osteogenesis, that surgical technique to lengthen bones.
Wow, so we're basically copying what nature already does. That's pretty awesome. How is that different from endochondral ossification?
This one's a bit more complicated. It starts with a cartilage model, kind of like a blueprint, that slowly gets replaced by bone. Most of the long bones in our body form this way. It's like we build a temporary scaffold out of cartilage and then carefully swap it out for bone.
So cartilage is like the unsung hero of bone formation then.
Haha. Yeah, you could say that.
What about appositional growth? Where does that fit in?
Appositional growth is how bones get wider. Imagine adding layers to a cake to make it thicker.
Okay, yeah.
Osteoblasts, the bone-building cells, they work under the periosteum, that tough membrane covering the bone, and they lay down new bone tissue, making the bone wider.
Got it. So I've covered the basics of bone formation, but let's talk about the physis, the growth plate. That's the powerhouse for longitudinal bone growth, right?
Exactly. And to understand how it works, we need to look closer at its zones. The resting, proliferative, hypertrophic, and metaphyseal zones, They all have a specific job in this growth process.
I remember using a mnemonic for those, RPHMDC plus MPS. Resting, proliferative, hypertrophic with its subzones, and then the metaphysis. Did I get that right?
You nailed it. Think of the resting zone like a pool of talented cells just hanging out in a low oxygen environment, waiting for their turn.
Okay, makes sense.
Then, in the proliferative zone, things get busy. Chondrocytes, the cartilage-making cells, they start multiplying like crazy in this high oxygen environment, pushing the bone to grow longer.
Sounds like a busy construction site at the cellular level.
Yeah, exactly.
What about the hypertrophic zone with all those subzones? That always seemed a bit more confusing.
It is. It's all about getting that cartilage ready to transform into bone. First, in the maturation subzone, those chondrocytes have a huge growth spurt and start storing calcium.
Okay.
Then, unfortunately, they undergo programmed cell death in the death subzone, but they release all that calcium they've been storing.
I see.
And finally, in the provisional calcification zone, all that calcium gets deposited, building the foundation for new bone.
So it's a perfectly timed cycle of growth, death, and renewal.
That's incredible, and we can actually see these zones under a microscope, right?
For sure. We use this special stain called safranin O that stains cartilage a bright pink so we can see all the changes happening in the physis.
Oh, cool. So more pink means more cartilage.
Yep, exactly. Like in the resting and proliferative zones.
That's a helpful way to visualize it.
Mhm.
But why does the physis only grow longer and not wider? If all those chondrocytes are dividing, why doesn't the bone just grow in every direction?
That's where the perichondrial ring of LaCroix comes in.
Okay.
This fibrous, bony ring wraps around the physis, kind of like a corset, and makes sure the growth stays in one direction, lengthwise.
Ah, so it keeps everything in line.
Exactly. If this ring gets damaged, you can get some really abnormal bone growth and deformities.
Makes sense. But all this growth needs a lot of energy, right? What about blood supply to the physis? How does it get all the nutrients it needs? The physis has 3 blood supplies, each with its own job. The epiphyseal artery supplying the secondary ossification center, the metaphyseal artery coming off the nutrient artery of the diaphysis, and the perichondrial artery feeding the perichondrial ring of LaCroix. They work together to make sure there's enough blood flowing throughout the whole growth plate.
So it's a whole network delivering fuel to those hardworking chondrocytes. This makes me wonder, what happens when something disrupts this system?
That's a great question, and it leads us right into the next part of our deep dive.
Awesome. I'm ready to hear more.
Stay tuned, because next we'll explore all those factors that can influence and sometimes even mess up this delicate dance of physical growth. So as we were just talking about, the physis is like this crazy complex system, and it needs this perfect balance to work right. Now we're going to focus on the things that can change how the physis grows,
Okay.
and sometimes even mess things up. You know, as ortho residents, this is where it gets real.
Oh, yeah, for sure.
This is the stuff we're dealing with every day.
Yeah, definitely. Hormones, nutrition, I'm guessing genetics plays a role too, right?
You got it. Hormones are like the big players, controlling growth all through childhood and adolescence. And each one affects the physis in its own way. Take PTH, parathyroid hormone.
Okay.
It has this direct mitogenic effect, which means it tells those chondrocytes in the proliferative zone, you know, the ones working hard,
Right.
to divide and multiply even more so the bone grows.
So more PTH means more growth. Seems pretty straightforward.
Well, it's usually true, but it's not that simple. It's more like a balancing act. Calcitonin, another hormone, actually does the opposite.
Oh, interesting.
It makes the cartilage calcify faster, which can actually slow down growth.
So it's a bit of a tug of war between them. What about thyroid hormone? That affects growth and development too, right?
Right. Thyroxine, that's the specific thyroid hormone. It's super important for everything to grow normally. It helps with DNA synthesis and cell proliferation.
Okay.
So if someone doesn't have enough thyroid hormone, their growth gets stunted.
Makes sense. And then there's growth hormone, the big one. That's like the main driver, isn't it?
Totally. Growth hormone comes from the pituitary gland,
Right.
and it acts on the liver to make these things called insulin-like growth factors, or IGFs. They're the real workhorses,
I think.
making those chondrocytes proliferate and differentiate so the bone can grow longer.
Yeah, so growth hormone is like the boss giving the orders, and the IGFs are the ones actually doing the work.
Yeah, that's a good way to think about it. And then we have the sex hormones, estrogen and testosterone.
Oh, yeah, those are important.
They really kick things into gear during puberty, causing that growth spurt we see in teenagers. But eventually, they also tell the growth plates to close up, which means our skeletons stop growing.
Those teenage growth spurts are no joke.
Yeah.
But I also remember learning about steroids and how they can be bad for bone growth.
Yeah, that's right. Using steroids for a long time can actually stop growth because it messes with cell proliferation in the physis.
Yeah.
That's why it's super important to keep an eye on growth in kids who have to take steroids.
It's fascinating how much these hormones control bone growth,
Hmm.
but it's also a little bit scary. What about other things like nutrition? That has to be important too, right?
Absolutely. Nutrition is all about giving the body what it needs to build those bones. Vitamin D, for example, is crucial for absorbing calcium
Yeah.
and for mineralizing cartilage in the physis. If you don't get enough vitamin D, you can get rickets, which is when the bones get soft and bendy.
Right, like those classic bowed legs.
Exactly. What about vitamin C? Any thoughts on what it does?
I know it's important for collagen,
You
right?
got it. Collagen is what makes cartilage and bones strong,
Mm-hmm.
and vitamin C is essential for making it. If you don't have enough, you get scurvy, which messes up the primary spongios of the bone.
Wow, so even something as simple as not getting enough vitamins can have a huge effect on bone health.
It really can.
We've talked about hormones and nutrition, but what about those growth factors you mentioned before? What do they do in all of this?
Well, besides those IGFs, there are a bunch of other growth factors like fibroblast growth factors or FGFs
Okay.
and transforming growth factor beta or TGF beta. They're like messengers telling cells how to act.
Gotcha.
They control everything from cell division and differentiation to how cells move around. Think of them like the foreman on a construction site, making sure everything is built the right way.
So it's like hormones, nutrients, and growth factors are all working together to make this bone growth happen. It's pretty amazing when you think about it.
It is.
But what happens when something goes wrong? Like when one of the instruments in the orchestra is out of tune?
Good question.
What are some conditions that affect different parts of the physis?
That's where knowing the physis really helps us in the clinic. Let's go through it zone by zone, starting with the reserve zone. This is where you see things like Goucher's disease and dystrophic dysplasia.
Right.
They both mess with how cartilage is made and can cause bone deformities. Dystrophic dysplasia is interesting because it can cause those cauliflower ears because of the weird cartilage growth.
Cauliflower ears.
Yeah.
Yikes, that's a good way to remember it.
Yeah.
What about the proliferative zone? What can happen there?
In the proliferative zone, we see things like achondroplasia, the most common type of dwarfism.
Right.
There's a problem with the FGFR3 gene in achondroplasia, which means those chondrocytes aren't dividing as fast as they should,
Oh, I see.
and the bones end up shorter.
So the problem is that the bones aren't growing fast enough. What other conditions affect this zone?
We also see gigantism, where there's too much growth hormone and the bones grow too much.
Okay.
And multiple hereditary exostosis, or MHE, where these bony bumps, called exostoses, grow out from the bone, usually near the growth plate.
So we've covered the reserve and proliferative zones. What about the hypertrophic zone? I'm guessing there are a lot of problems that can happen there since that's where the cartilage is maturing and calcifying.
You're right. The hypertrophic zone is a common place for problems. We see things like rickets, which we already talked about,
Right.
and Salter-Harris fractures, which are fractures that go through the growth plate.
Salter-Harris fractures are definitely something we need to know for our exams. And I remember there are different types depending on where the fracture is in the physis.
Exactly.
Okay.
And the type of Salter-Harris fracture tells us how likely it is that the bone will have problems growing later on.
Right.
Another condition in this zone is slipped capital femoral epiphysis, or SCFE.
Oh, yeah, SCFE.
That's when the head of the femur slips off the neck of the bone at the growth plate.
SCFE is another one that can have serious consequences if you don't catch it early.
Yeah.
What about the primary spongiosa? What kind of things go wrong there?
The primary spongiosa is where we see the effects of scurvy, remember?
The vitamin C problem.
Without enough vitamin C, the collagen can't form properly, so the bone in that area is weak and more likely to fracture or deform.
So scurvy really affects the primary spongiosa. What about the secondary spongiosa?
In the secondary spongiosa, you can see things like renal osteodystrophy, which is a bone disease that happens in people with chronic kidney disease. It's caused by a bunch of hormonal and metabolic problems that mess up how the bone mineralizes and remodels.
Gotcha.
We also see osteogenesis imperfecta, or OI, which is a genetic disorder where the bones are really brittle and fracture easily.
Right, OI.
That's because the collagen isn't made right.
Wow, we've covered so much, and it's amazing how many things can affect the physis. It really shows how important it is to understand how it works. Before we go on, let's just remind everyone about those Ortho Made Simple notes from mokyingren.sg. They've been super helpful today. Dr. Mokyingren, the guy who made these notes, he nailed his FRCS back in 2022, so these notes are gold for any ortho resident getting ready for their exams. Okay, so we're back and ready to wrap up our deep dive into the physis. It's been pretty intense, all those details.
Yeah, it has. We went from the very beginning, like how limbs even form,
Right.
all the way to those tiny zones in the growth plate and what can throw them off balance.
Let's test your knowledge. Quick challenge.
Yeah.
Think about the bones in the hand, the metacarpals and phalanges. Where are their physes?
Ah, that's one of those classic anatomy questions they love to throw on exams.
Exactly.
But I'm ready for it. The physes in the hand are at the proximal ends of the phalanges and the distal ends of the metacarpals.
Nailed it. It seems kind of backwards compared to most long bones,
Yeah.
but it's so important to remember, especially when you're dealing with fractures in kids' hands.
Absolutely. Knowing where those physes are is key for diagnosing and treating hand injuries in kids,
Yeah.
especially if you're worried about growth problems.
Okay, let's do a quick recap of what we covered today. We started with those three main pathways, the AER, ZPA, and WANT.
Right.
They're like the guiding forces for how limbs develop from the very start.
Yeah.
Then we talked about how bones form, those three ways:
Yeah.
intramembranous, endochondral, and appositional growth.
Mm-hmm.
And we spent a lot of time getting into the nitty-gritty of the physis itself.
Yeah.
All those layers and zones, each one with its own important job, and that amazing process of how bones grow longer.
It's pretty cool when you think about it.
Definitely. We also talked about what can affect growth in the physis.
Right, like those hormones.
The hormones and all those nutrients, especially vitamins D and C, and how problems with those things, whether it's genetics, hormones, or what we eat, can cause all sorts of orthopedic conditions.
Don't forget those Ortho-Made Simple notes from mokyingren.sg. They've been a huge help today. Dr. Mokyingren, who wrote these notes, he clearly aced his FRCS, so they're a must-read for anyone studying for their orthopedic exams.
Totally agree. So as you keep studying for those exams, think about how everything we talked about today connects to what you see on x-rays,
Yeah.
how you figure out what's wrong with a patient, and how you decide on the best treatment.
The physis, it's more than just a growth plate. It tells us how the skeleton develops and helps us understand all kinds of orthopedic problems.
That's a great way to put it. Remember, there's always more to learn. Keep asking questions, stay curious, and never stop exploring the world of orthopedics. Thanks for joining us on the Deep Dive. We'll see you next time for another exciting adventure in knowledge.